Richard Bleiel, okay, you know what, fine. Maybe I'm not your all-time favorite, but you're watching my video, aren't you? Bite! Anyway, today we're going to be talking about pee. No, look, I know a little bit about pee because of my age. I do have a little bit of bladder control, but that's not the kind of pee we're talking about. No, today we are talking, and I'm going to have a little preamble for you too. Today we're talking about pH. We have kind of a problem in modern society where if people don't know something, they just make stuff up. And I'm not just talking about videos like the one I saw on my social media page. I'm talking about teachers, professors, supposed experts in their field, authors who write textbooks even for upper level chemistry subjects, and the publishers and their editors who let these things slide. Look, there's a reason that things are the way they are. Don't make stuff up. Here's the preamble for this. I was sort of scrolling through my favorite social media site. I'll give you a hint. No, it does not. It is not owned by anyone with the name Elon. And I happen on a reel. And boy, this kid was excited because he figured out what pee is. He was so excited and so ready to share what he learned with you because throughout his whole life, he knew that pH was a measure of acidity. And he knew that the H stood for hydrogen. No. H does not stand for hydrogen. We're going to cover that in this video as well. But no one ever told him what P is. Nobody knows what P stands for. And he actually quoted what he said was the original article where pH was suggested as the scale to use. But I'm going to be honest, I did not go and look up that article. But he claimed that the author said, well, look, this is what we want to use, and he never explained what P is, even in the original article. And he went on to say, I now know what it is. P stands for the power of the acid. God, no. P does not stand for the power of the acid. It kind of stands for power, but not in the way that you're thinking. It's a different kind of power. It's not the power of the acid. And here's why. Here's how I know that. If you know the pH scale, and a lot of people do, you know that it's a scale that runs from 0 to 14. Has a hypothetical limit of 0 and for the strongest, and a hypothetical limit of 14. I say hypothetical because it's impossible to get an acid or a base that goes to the extremes, unless you have what's called a superacid, which is well beyond the scope of this particular video. Very rare. But here's why P does not stand for power. If you know the scale runs from 0 to 14, you probably also know it's an inverted scale. That means that the smaller the pH, the stronger the acid. Are you honestly telling me that the most powerful acid you can have has 0 power? Does that make any sense at all? So if pH does not stand for power, at least not in the way you're thinking, what does it stand for? Well, before we talk about that, let's go back and talk about what acids and bases are. I'm going to be using specifically today the Arrhenius definition, which I think is spelled like this, but for some reason I'm not 100% certain. The Arrhenius definition. It is the simplest definition of acids and bases. There are at least 2 additional definitions, and I know there's more than that if you get into really high-level stuff. But this one is fine for our purposes today because the Arrhenius, which is the original definition of acids and bases, the Arrhenius definition is based on the auto-dissociation of water. Auto-dissociation does not mean you parked in the wrong part of town and came back to only part of your, like the frame of your car. No, that's not what auto-dissociation means. Auto-dissociation refers to the fact that water automatically dissociates. Water, H2O, it dissociates into hydronium ions, not hydrogen. Hydronium ions, that's what the H stands for, hydronium ions, and hydroxide ions. Now, right now, someone is pulling their hair out and saying, "You're wrong, you're wrong, you're wrong." Give me a second here. We're going to address why they think I'm wrong, and I'll show you why I'm doing it the way I'm doing it. There's a reason I'm doing it this way. Believe it or not, I know what I'm doing. But, first of all, let's talk about this funny little symbol here. You may notice that symbol is not your straightforward one-way chemical reaction symbol. This double-headed arrow here, double-sided arrow actually, not double-headed, this double-sided arrow represents an equilibrium. That means that the reaction is occurring in both the forward and the reverse direction at the same time. At the same time. Equilibrium, by definition, is no observable change over time. It doesn't mean that the reaction has stopped. It means no observable change. In other words, if you could measure the concentration of your hydronium and hydroxide ions, which you can, we're going to talk about that here in a second, what you would find is that they're steady. They're not changing. But although they're not fluctuating up and down, the reaction is still occurring, but it's occurring in the forward reaction just as fast as it's occurring in the reverse direction, which means you are not going to notice a change in equilibrium. No change over time. It's like my bank account. As a semi-retired professor, see, there's my degree right there. You can't see it, it's off the screen. Anyway, doesn't matter. As a semi-retired professor, I now work at a low-stress drive-in theater. Yeah, low stress. We're already sold out for this week's shows. It's not low stress, but yeah, it's lower stress than being a professor, I'll tell you that. Anyway, for my services, I make, let's say, $37 a week. Okay, I make a little more than $37 a week, but Lord, not much. But that $37 goes into my bank account every week. The problem is every week I have a powerful need to eat food. So, and to pay for lights, and to pay for my phone, and my internet, which is I'm going to upload this video. As it turns out, I pay exactly $37 a week in my bills. Does it stop? No. But I have $37 going into my bank account. I have $37 coming out of my bank account at exactly the same rate. So how much does my bank account change? Over time, you're not going to see any fluctuation. It stays where that bank account is at negative $48. Not going up, not going down. Steady, equilibrium. That's what this is. The water is falling apart to produce hydronium and hydroxide ions. The hydronium and hydroxide ions are combining to form water at exactly the same rate. So over a period of time, you're not going to see a change in concentration. Here's where the people who are screaming their heads off or screaming their, here's why. If you think about what the hydronium is, hydrogen is just one proton and one electron. Now there's two isotopes of hydrogen. They're the only isotopes on the periodic chart that have unique names. Deuterium is one proton, one neutron, and one electron. Tritium is one proton, two neutrons, and one electron. Tritium, three nuclear particles, one proton, two neutrons. That's where tritium's name comes from. Deuterium, one proton, one neutron, two nuclear particles. But mostly, and for a vast majority, hydrogen is just one proton, one electron. Well, it has a positive charge because it lost that electron. The electron is negatively charged, so taken away, you are left with a positive charge. So what is a hydronium ion? Well, the way I've written it up here, it looks like the hydronium ion is really nothing more than a free-floating proton. It's not. Free-floating protons do not exist. So a lot of professors and authors, in order to be correct, will write an extra an extra water molecule here to give a different type of deuterium. Now, the extra water molecule, actually I'm going to write it out. So we have H2O plus H2O, or if you prefer, 2H2O What's happening? Well, the hydronium ion from one of these waters is going to go and associate itself with the oxygen of the other one. So it's going to form, however you wish to draw this. So it's going to form H3O+. And you're still left with that hydroxide ion. And all those people screaming about the way I wrote it are going to say, there, that's the right way. No, as it turns out, that's not the right way. Read your literature. As it turns out, spectroscopic studies have demonstrated that hydronium really does not associate with just one water molecule. It can associate with 2 water molecules, 3 water molecules. It forms like a little cluster. If it associates with 2, then you're going to have, let's see if I get this right, H5O2+. 3 would be H7O3+. In fact, spectroscopic studies have demonstrated that the most common form of hydronium ion, this is a disturber listening to, thank you. The most common form of hydronium is 4 water molecules, H9O4+. So when you think H3O+ is correct, it's not. H4O9 is the closest you're going to get to being the correct and actual cluster that you get. And yes, there are larger clusters as well. H11O5+. But the point I'm making here is that H3O+ is no more correct than H+. This is just a representation of the hydronium ion. And if H3O+ is no more correct than H+, why am I complicating the picture with an extra water molecule? There's no reason for it. It is no more correct. So therefore, I choose to represent my hydronium ion as H+. I recognize that is not the way it really is, but I also happen to recognize that the normal way hydronium is written is not correct either. Okay. When we're talking about acids and bases, we're talking specifically about water solutions. Why does water get its own special treatment, its own special, why do we treat it separately? Well, it's because of how important water is to us. As human beings, our bodies are 90% water. Unless you drink too much Diet Coke like I do, in which case I'm really severely dehydrated, I'm down to 17% water. If a fly flies into me too hard, I'm going to crumble into dust. The earth is covered by 70% water. Water surrounds us. It's in the air. It's everywhere. So water is very important to us as human beings, and as a result, it gets special consideration. So what makes an acid? Now, any water-based solution like this Diet Coke, it is undergoing this autodissociation. Always. Always, always, always. So what's an acid? An acid simply has more hydronium ions than it has hydroxide. That's an acid. It doesn't mean it has no hydroxide, it just has an excess of hydronium. A base has an excess of hydroxide, but it still has hydronium, even though it has more hydroxide than hydronium. That's a base. That's all it is. Now, as chemists, we can write what's called an equilibrium constant expression for this autodissociation. This stuff is terrible. And it looks like this. Anytime we write an equilibrium constant expression, we leave out water. Because water is so prevalent, its concentration doesn't really change, so we just take the concentration and factor it into the equilibrium constant expression. So we have an equilibrium constant expression. Looks like this. Now, if you want to play along, grab a calculator. If you're a math file like I am, if you don't want to grab a calculator, or if you do, make sure it has a base 10 log, but L-O-G. If you don't want to, that's fine. You'll just have to take my word for it when I do the calculations. These square brackets represent concentration. Now, specifically, if you're a chemist, if you know a little bit about chemistry, specifically, it stands for molarity as the concentration unit. But we're not going to worry too much about that. It just means concentration. So the equilibrium constant expression is the concentration of hydronium times the concentration of hydroxide. This is for water. Therefore, since water gets special consideration, we're going to put a subscript W here to say, okay, this is the equilibrium constant expression, and that's my cat Star showing up to say hello. Anyway, equilibrium constant expression W. Yes, I'm a childless man with cats. Anyway, this is just the concentration of hydronium times the concentration of hydroxide. As it turns out, there's a reason this is called an equilibrium constant expression, because it's a constant. It is an experimentally measurable constant, and it has a value (1.0 times 10 to the negative 14th power). Oh, is that starting to look a little bit familiar to you? Yeah, you're right. The 14 here corresponds to the 14 in the pH scale. Good call, Star. I'm impressed. So this is experimentally measurable, which means if we know the concentration of hydronium or hydroxide, if we know either one of those, we can find the concentration of the other just by plugging it into this little equation. Okay, finally. So what is P? P, as it turns out, is a mathematical formalism. Now, my mathematics friends may know better what it actually stands for, but it's just a way to handle particularly small numbers, like 1 times 10 to the negative 14th. Write this out so it's not in scientific notation. It becomes 0.000000000000001. It's just a very small number. And if I don't want to write scientific notation all the time, I can simply write the p value. If you have a very small number, x, whatever that number is, the p value of that number is defined to be. It's not derived. This is a mathematical definition. It is defined to be negative log of that number, base 10 log. Why is the pH scale negative? Where lower the number, the higher the concentration. It's an inverse scale because of that negative sign right there. That makes the pH scale an inverse scale. No, I don't love you, go away. Go away, you are not the star. You are not the star. Now, that means that pH, by definition, is negative log of the hydronium ion concentration. That's all it is. A number of years ago, had some lab tests done. I had a heart attack at 47. And it's because I drink stuff like Diet Coke. Anyway, I'm terrible. I'm not married. So there's no reason for me to eat healthy. So I don't. So anyway, on the lab results, I saw something, PNA. What I saw was PNA. Well, NA, say hi, Star. Hi, Star. Boy, she is upset. Okay, fine. Well, let go and I'll put you down. Anyway, Na is the atomic symbol for sodium. What they reported on my labs were my sodium levels using a pH scale, using a PNA scale, negative log. Now, here's the curious thing. If you know pH, you're actually being given the concentration of the hydronium ion. Because for every mathematical function, there's an anti-function. If you want to know the actual value of that number, x, it's just 10 to the negative px. Now be a little careful here, because this is not scientific notation. Okay, I'm in trouble. There it is. My calculator, scientific notation, oh, you can't even see it, is this little key right here. It's EE. That's the key that you press for scientific notation. But if you look at log, which is actually a second function, usually the second function of log is 10 to the x. That's what I'm talking about. This is the anti-log, not scientific notation EE or whatever your calculator says it is. A lot of students get this wrong, and if you push the anti-log when trying to use scientific notation down here, sometimes you're off by a factor of 10. So make sure that you're using your calculator correctly Find the key specifically for scientific notation. Don't press the mathematical function times. Don't use anti-log. There's an entire key on your calculator that means specifically 10 to the for scientific notation. One button, so you're saving yourself time, and by doing it correctly, you're less likely to be slipping that decimal point. Okay, that means that if we want our hydronium ion concentration, just take the anti-log of your pH. So I said that maybe P does stand for power. Maybe. What do I mean by that? Let's do a couple of quick examples. And by the way, notice, once I have my hydronium ion concentration, I can plug it in this equation. Equals 1 times 10 to the negative 14th, divide, and I get the concentration for hydroxide. So if you know the concentration for hydronium from pH, you also know the concentration of hydroxide from this equation. Okay, so let's do a couple of examples. Let's do one example first of all. Let's talk about a neutral solution. I told you this, I told you this, I told you this. In an acid you have excess hydronium ions, in a base you have excess hydroxide ions. In a truly neutral solution, and we allow for a little bit of fluctuation, but in a truly neutral solution, your hydronium ion concentration, so this is only true at neutral, your hydronium ion concentration is exactly the same as your hydroxide ion concentration. Star did not like being picked up for the video. She has buggered off. Well, if that's the case, then Kw, we can substitute H plus into this equation for OH minus. And we get this. If we take the square root, we will see that our hydronium ion concentration is equal to 1 times 10 to the negative 7th. What is neutral in the pH scale? It's 7. If you take the log of 1 times 10 to the negative 7th, you get negative 7. But we're going to reverse that sign. This simply becomes 7. That's why neutral in the pH scale is 7. Mathematically, it becomes 7 based on experiment, based on this experimental value. Now, as it turns out, it's kind of what I was talking about. The P may well stand for power, because you do get 7. This is only going to happen if you have 1 in this position. Any other number is going to give you a value different from what you have here, although it may be close. It will be close. It'll end up being from 6 to 8, so it'll be somewhere in the neighborhood, but it's not going to be the same. And why is it, by the way, that this inverse scale means a smaller pH more acidic? Well, let's look at this. Let's take two cases. Let's take an acidic pH of 2 and an alkaline pH of 9. I'm using integers here. You don't have to, but for this example I am. Well, using this formula, we get 10 to the negative second power. Whereas down here, it's 10 to the negative ninth power. Or 0.01, as opposed to this one, which is 0.1, 2, 3, 4, 5, 6, 7, 8, 9. You can see that pH of 2 has a much higher concentration of your hydronium ion than the pH of 9. When you're working with scientific notation, you have to remember to consider the power first, as opposed to the actual number. I'll give you an example. Here's a common mistake. Let's do it the other way. Suppose we have a hydronium ion concentration of 7.8 times 10 to the negative 12, and another solution with a hydronium ion concentration of 3.4 times 10 to the negative fourth. If I ask you which one of these numbers is more acidic, which one is bigger, it's an easy mistake to say, well, 7.8 is bigger than 3.4. Therefore, it's the bigger number. But that would be wrong. Because 12 is so much bigger than 4. And notice we have a negative in front of it. So 10 to the negative fourth, 0.00034, is much, much bigger than 0.00000000078. You have to consider the powers. And this is where I think that perhaps P does stand for power, but not the strength, not the power. Not like, oh, the acid is so powerful. No, 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 no. It stands for this power. Because if I actually take the pH of these two examples, well, let's do it, and you'll see what I mean. So, if you have a calculator, play along. The top one, the pH, and what we're going to find is that this pH is going to be close to but not equal to 12. This pH is going to be close to but not equal to 4. So it's very close to the mathematical power of the concentration. Let's do it for real. Like I say, if you want to play along, 7.8 times 10 to the negative 12th. This pH is, whoa, that's not right. Let's try that again. 7.8 times 10 to the negative 12th. That is wrong. Oh, what an idiot I am. That's all right. You can call me an idiot. This is 11.1. Like I said, not exactly equal to 12, but close to it. Notice it's larger than 7. That is alkaline. That's basic. For the number below, 3.4 times 10 to the negative fourth, we're getting 3.47. Less than 7, close to the negative 4, definitely acidic. If you're a teacher and you don't understand something, look for the answer. Don't try to guess about what something might mean and teach the wrong thing. If you can't find it, just admit to your students, you know, I am not sure what that P stands for. If you honestly don't know, there's nothing wrong with that. You are not gods. You're allowed to not know some things. That's okay. Then you can make it a challenge for your class. You know what, class, if you can figure this out, let me know. I would like to know. I used to do that all the time when I taught. You ask a question that I'm not sure of. Notice that, well, this one is kind of close to the 3.4. That is coincidental. That is coincidental. That normally does not happen. But notice 11.1 is not the same as 7.8. But now you understand, first of all, what an acid and a base is, how they're related. Now you understand what the P means in pH, that it might be power, but not power as in strength. It's not what it represents. And I think this is the second time I made this video because I had a technical failure, a glitch, last time I made this. So I'm using a different camera. The original camera's recording right over there, so that if this one fails, then I have that one as a backup. If that one fails, I have this one. This is my main one. So I'll tell you this right now. I am out of here.